This video is all about a sample problem of first law of thermodynamics with fluid mechanics in an open system application. Now, the problem is water with a density of 1,000 kilogram per cubic meters from a non-elevated open reservoir. Okay? The pressure of the non-elevated open reservoir is 0 bar. Flows before the pump at 1.5 meters per second. The water is pumped at a rate or velocity of 30 meters per second to a 20-meter elevated tank with a pressure reading of 1.02 bars. Assuming zero frictional losses, calculate the actual work if the pump's efficiency is just 69%, and then calculate the theoretical and actual power in horsepower for a mass of water at 100 kilograms and a time of 1 minute of water. Now we are given with the following conversion factors as a horsepower is equal to 746 watts and a bar is equivalent to 100,000 of pascals. Now let's enumerate the following given parameters. The density of the water is 1,000 kilogram per cubic meter. And if we're going to illustrate the problem, we are given with a non-elevated reservoir. Okay. So obviously the elevation is 0 meters, or H1 is equal to 0 meter. And the pressure of the open reservoir is at P1 is equal to 0 bar. The velocity of water flowing before the pump, V1 is at 1.5 meters per second. Now, let's consider the parameters of water flowing after the pump. The velocity is at 30 meters per second, so this is V2. And the height of the tank is equal to 20 meters. The pressure reading of the tank is at 1.02 bars, and the pump efficiency is equal to 69%, or in decimal, that is 0.69. And then the analysis of the water at 60 seconds or 1 minute, we're going to use 100 kilograms as stated in the problem. Now let's proceed. Now we are required to determine theoretical and actual horsepower of the pump. Now, how are we going to do that? Now, after illustrating the problem, if we're going to analyze again the problem, we are given with summation of frictional losses is equal to 0. Okay, assuming zero frictional losses equal to 0. So the next analysis we're going to consider is the fluid head. The fluid head is dependent on the amount of change in pressure and density of water for the whole systems of 1 and 2. Now, the formula for fluid head, delta P all over rho, or delta P all over the density, is equal to the pressure at the second tank minus the pressure at the first tank. Okay, so this is in quantity. Multiply it with the amount of water for the analysis all over the density of the water. Now, if we're going to substitute the following parameters, this gives us 1.02 minus 0 for P2 minus P1. Multiply it with the following conversion as bar, bar, and 1 bar is equal to 100,000 pascals, and a pascal is equal to 1 Newton per meter squared. Multiply it with the given mass of the water for 60 seconds is at 100 kilograms, all over our density for the water for this problem is a 1,000 kilogram per cubic meters. Now, the final answer gives us 10,200 Newton meter, or this is in joules. Now, the third parameter we're going to consider to calculate is potential energy. Okay. Potential energy is equal to mass times gravity times delta H. all over the gravitational constant. Okay. So if we're going to expand the formula, this is mass times gravity, okay, multiplied with h2 minus h1, or the height 2 minus height 1, all over the gravitational constant gc. Now, if we're going to substitute the following values, the mass is at 100 kilograms multiplied with Earth's gravity at 9.8 meters per second squared, multiplied with the following changes in height as 20 meters minus 0 meter, all over our GC at 1 kilogram meter per Newton second squared. Now, further simplifying the following quantitative values, this gives us 19,600 Newton meter or joules for potential energy. The fourth one to be solved is the kinetic energy for the following fluid system. So delta KE, or delta kinetic energy, or change in kinetic energy, is equal to mass times the velocity or final velocity v2 squared minus the initial velocity v1 squared, all over twice of the gravitational constant gc. Now, plugging in the values, this gives us 100 kilograms multiplied with 30 meters per second quantity squared minus 1.5 meters per second quantity squared. Take note, these velocities are in state 2 and state 1. So this is the final velocity after the water flowed through the pump. So this is at 30 meters per second. And the initial velocity of prior the water flow prior the pump. Okay, so this is at 1.5 meters per second. Okay, quantity squared all over twice GC. So our GC for SI unit is 1 kilogram meter per Newton second squared. So further simplifying these values for kinetic energy gives us 44,888 Newton meter or joules. To solve now for the theoretical pump work, okay, so the theoretical pump work, or W prime, is equal to our fluid head plus kinetic energy plus potential energy plus the frictional losses. Now, substituting in the values gives us, okay, 19,600 plus 44,887.5 plus 10,200 joules. Summing these following terms gives us a value of almost 75,000 joules for the theoretical pump work. Now, to solve now for the actual pump work, we're going to divide our W prime, or theoretical pump work, with the amount of pump's efficiency. So 74,687.5 joules all over 0.69 gives us 108,242.75 joules. And then for the actual power, or actual horsepower of the pump, so we're going to use this. So the work actual per unit time of 60 seconds, okay, since this is given at the problem, 1 minute. So you're going to convert it to seconds times a watt all over 1 joule per second multiplied with this conversion as 1 horsepower is equal to 746 watts. Okay, so the watts cancels out, gives us a horsepower. So the pump is very powerful. It is equal to the power of 2.5 horses. Okay, so exactly, it's 2.42 horsepower. So that concludes our topic for today. Our next video, we're going to discuss the calculations for electrochemical cells.